Yeah, so it is easy to show that phi is continuous from r minus, so for sub I to I, what is I? He is continuous, and phi of r is r, means it r is a fixed point where r is a root of f. Okay, and what is I here is I is equals to neighborhood of r minus delta to r plus delta. Okay, so it can be shown that phi is continuous because it's a sum of two continuous functions. You know that rational function is continuous whenever numerator is continuous and denominator continuous, and it continues everywhere except where the denominator vanishes. So you know that f dash of r is non-zero, so you can take a very small neighborhood of r where f dash of r remain non-zero. So you can show that f of p of x is continuous on this interval. So you can choose delta in such a way. So and it can be shown that phi maps I into I. Okay, now let's calculate phi dash of x for this case. So phi dash of x is equals to, if I take u upon v rule, f dash of x whole square. So f dash of x time 1 minus f dash of x plus x minus f of x time f double dash of x. Right? Now you need to have phi dash of r. I need to see what is the phi dash of r. Okay, I have done a mistake here. This is, if you take the LCM, it is x time f dash of x, right? So you have, let's correct it here, f dash of x time, so if I write here x time f dash of x minus f of x divided by f dash of x. So f dash of x time derivative of this numerator, that is x time f double dash plus f dash minus f dash plus not plus, it's minus x time f dash, okay, minus time f double dash. Right? So now you can see that x time f dash of x f double dash will get cancelled with this, with minus sign. F dash of x will get cancelled here, and what you will have, minus minus plus. So what you will have is f of x time f double dash divided by f dash of x whole square. So which certainly imply phi dash of r is 0. If you evaluate at r, phi dash of r is 0 because f of r is 0. Okay, because f of r is 0, so phi dash of r is 0. So first derivative of phi at r is 0. Now you will go for second derivative, okay, and see that whether phi double dash of r is non-zero or not. So what we have just now obtained is phi dash of x is equals to f of x into f double dash of x divided by f dash of x whole square. Now you take again second derivative of this, that is f dash of x to the power 4. So f dash of x whole square time the derivative of this f of x into f double dash. So f into f third derivative plus f dash into f second derivative. This is an absurd notation I just try to use because x is silent now, okay, minus f into f double dash and derivative of f dash of x whole square is 2 times f dash time f double dash, okay. So it is giving 2f time f dash time f double dash square, okay. Now evaluate at phi double derivative at r. So since f of r is 0, so this term will go 0 and this term will also go 0, right, because f of r is 0. So what you will remain with is f dash square time f dash f second derivative, that is the only term survive in the numerator, divide by f dash to the power 4, which is equals to f second derivative at and divide by f dash, and which is non-zero because both are non-zero at r. So what it says, so this says that phi first derivative is 0 but phi second derivative is non-zero. So this implies the order of convergence is 2 and a n plus 1 is equals to 1 by 2 factorial, right, e n to the power square time phi second derivative at r, that is f double dash at r by f dash of r. So this is what only we obtain at the starting state, right. This is what approximate, okay. Now showing that this shows that Newton's method has quadratic convergence, okay. What we need to show that mod of xn plus 1 minus r is less than equal to c time mod xn minus r whole square, okay. Now, okay, so phi dash of x, so magnitude, so for this mod of phi dash of x less than 1, so if you impose this condition mod of phi dash of x less than 1, okay, then you can apply the Picard fixed point theorem, which says that, okay, which says that this is your maximum, okay. So because here f of x is continuous over closed interval ab, f double dash is continuous, f dash is continuous on closed interval ab, its complete function is continuous over closed interval ab. So it's these are continuous, okay. Okay, so phi dash is continuous on closed interval ab. So if a function is continuous on a closed interval, then it's uniformly continuous and it attains its bound, Okay, right. So that suppose that bound is strictly less than 1 L. Okay, that you need to assume that this is strictly for any x, this is strictly less than 1. Okay, so that will, okay, so that will, so here phi dash of x here is where x lies for the interval I, r minus delta to r plus delta. Okay, so it says that phi dash of r is 0 and this is phi dash of this is continuous, so it is showing that this is however small only, but what will be the value? Less than 1. It will be certainly less than 1. Okay, so let's say this is less than equals to L, and that L or C, okay, that you can use. Okay, so just now we have seen that P is a, so this will imply the Picard-Fix theorem tells you that this is, so let's assume that here, so what we have here is, so let's do this here, define phi of x, then phi of r is r. So phi is continuously differentiable and mod of phi dash of x is small near r, say in neighborhood, so it's small near r. Okay, so that is how small means very means because this tending to 0 as x tending to r. Okay, so means let's say mod of phi dash of x, okay, phi maps I into I, so let's see. So define a quantity C of delta dependent on delta by this. So we are assuming that mod of phi dash of x is less than equals to L. Okay, right, fine. Okay, so now define a quantity here C of delta dependent on delta by this. Okay, so what is this is, so if you recall that C constant, that is 1 by 2 factorial f second derivative at Zn divide by f dash at some eta n. Okay, right. So now where Zn and eta n were lies in zeta n is lies between and eta n are lies between xn and r, right, if you recall. So means in the neighborhood of r only. So what you have taken here, so instead of approximation you have taken this in the neighborhood of I, in interval I. So you require a new C which is maximum now, C of delta. Delta is of course depending on delta. So how will you make the more appropriate bound is you can take the maximum of numerator and take the minimum of the denominator over that interval I. Then it will give you a new quantity C of delta which is depending on delta. Okay. Now see, delta is in your hand. So what you can do is you can decrease delta if it is necessary such that delta into C is less than 1. Delta into C of delta is less than 1, or that you will call as, let's say, L. Okay, so you can decrease delta in such a way that delta times C of delta is less than 1. Okay, so what you have here is now is if necessary we decrease delta. So then it is easy to show that that mod En is less than equals to rho to the power n time mod E naught. What is rho here is rho is equals to delta time C of delta. So it is very easy. Just now we have seen that mod of En plus 1 is less than equals to C time mod of En square. Right? We have seen that. Okay. Now what, so from here what you have is mod of E1 is less than equals to C time mod of E naught square. What is E naught is mod of x naught minus r. Okay, mod of x naught minus r. So you can choose x naught and x naught minus r such that mod of x naught minus r is less than delta. So what will happen is, so this is equals to less than equal to c time, so if I rewrite this equals to c time mod of e naught time mod of e naught. So mod of e naught is less than delta, so this is less than delta times c time mod of e naught. Similarly, so delta times c you can, so this is mod e1. Okay, now use this fact now for, so now use this fact now to get the bound of mod of e2. So what is mod of e2 is less than equals to c time mod of e1 square, which is c time mod of e1 time mod of e1, right? So this is further less than equals to c time delta mod of e1 is mod of e naught, and mod of e1 is again c of delta square time mod of e naught. Right? So, okay, so what you will have here is and so on. So here what you can show is mod of, here is it's missing, here is mod of c time en here. Okay, so if you multiply c by here both side, what you will get here is c to here c square, so c square delta to the power. Okay, right, I think so. This is here c is missing here. Okay, right. So similarly you can have, so here is similarly here c here will be present there. Okay, so delta c, so this first case is, let's say this is rho is less than 1. Now in the next case, okay, in the next case here this is in the 4. Similarly mod of e3 is less than equals to c time mod of e2 square, and mod of e2 square is less than equals to, okay, this is c time mod e naught, that is here can we control some way so that it can be written, because initial approximation is in our hand. Okay, and mod e naught is less than delta, that's fine. Okay, so this is less than rho time mod of e naught. Okay, now mod of e2 is less than equal to c time mod of e1 square. Okay, c time mod e1 is okay c time, so here this is missing here, c time mod en is less than equal to rho to the power n time mod of e naught. So what we have here is as follows. So we can control the delta in such a way that mod of x naught minus r is less than delta, that is true. Okay, and mod en plus 1 is less than equal to c time mod of en square. That also we have seen. What is c is, we know 1 by this 1 by 2 factorial time maximum of this C of delta now. So L delta is chosen. So this is further bounded. So over the interval we are looking I. Okay. So okay. Right. So this is further what you will get here from here is mod of En is less than equals to, so this is mod of E2 is less than equal to C time, wait a minute, so mod E1 is less than equals to rho time mod E0, right? So rho square time mod E0 square here. Okay, yeah. So okay, let's do in fresh space here. So what is we having is a mod of E1 is less than equal to C time mod of E0 square, which is equals to C time mod of E0 time mod of E0. Right. So you can certainly choose delta or you can certainly start with initial approximation such that mod of x naught minus r is less than delta. Okay. So this is means this is E naught. Mod of E naught is less than delta. So this is less than C time delta mod of E naught, which is equals to rho time mod of E naught. Right. Now, what about mod of E2 square now? Mod of E2 is less than equals to C time mod of E1 square, okay, is equals to C time mod E1. So, mod E1 square is less than equals to rho square time mod E0 square. Yeah, okay. So, yes, so this implies certainly less than equals to C rho square time mod of E naught square. Okay. Now, what is happening here is mod of E naught into mod of E naught. So, this you can write this is equal to C time rho square time mod E naught time mod E naught. Mod E naught is less than delta. So C time delta is again less than equals to rho. So is equals to rho cube time mod E naught. Right? Okay. Now what about mod of E3 is less than equals to C time mod of E2 square is less than equals to C time rho cube mod of rho to the power 6 mod of E naught square, which is less than equals to rho to the power 7 mod of E naught this one, right, and so on, right. So what you are getting is, I think here is 2n plus 1, okay, or yeah, 2n minus 1, right. No, but here is 2n plus 1, okay. So odd powers, so 1, 3, 7 and so on, so increasing, right, okay. Okay, what you are getting is rho to the power 2 to the power Okay, so the generalized one we will see. So and so on, right? So this is how you can show that so here you need some modification. What will be the actual things I will come out with the in the next lecture. Fine. Okay, so you can show that means with the help of this, how many iterations in Newton's method are required for Newton's method in order to obtain root 2 with 10. So it completely depends on this inequality. So we will come out with this in the next lecture. Fine. Yeah. So I think here we will add okay, so here we will bind up the solution of non-linear equations. Fine. Okay, thank you.